Okay, so now we are going to go over a vector negation. So if I have a vector v, a free vector v, then actually I'm going to show you what happens when we don't say that v is non-zero. So v is a free vector. And I'm going to define vector negation as minus the free vector minus v, which has the opposite direction as v, but the same length. Okay, the problem with saying that v is a free vector is when we mentioned direction, because 0 is a free vector. However, we've defined it as having no direction, or an undefined direction. So we have to change this up and say that v is a, should I just rewrite it? No. V is a non-zero free vector. However, we need to have it, so we're going to have a separate definition for the zero vector. So v is a non-zero free vector, denoted minus v, which is in the opposite direction as v, but has the same length as v. Now the zero vector, which we'll say is minus, this is how we will define the negation of the zero vector. If we negate the zero vector, we get the zero vector back. Now, let's see how this links to bound vectors again. If I have the bound vector AB, and AB represents the free vector K, then, as we said, vector negation, the negation of the free vector is the free vector with minus k, which has the opposite direction, but the same length. Now, if we look at this bound vector AB, the same length but opposite direction would just be the bound vector BA. Oh, these are meant to be the same length. If I draw. So what we can draw from this is that if AB represents the free vector K, then BA represents the free vector minus K.